Swayam Prabha. Digital India. Educated India.
So, in yesterday's class, I was talking about lamella separator, which is used for water treatment. So, here the objective is to predict the minimum length which is required to settle all the particles, and also to predict the settling rate. We have already discussed this. So, here we consider the, so this is the physical model, and we choose the coordinate system appropriately. So, now we have, we calculate the, this I have discussed in yesterday's class. Okay. So, we first calculate the volume fraction from the mass loading ratio which is given, and from there we can calculate the average velocity of the fluid. Then we can calculate the particle injection rate, and then to find the particle trajectory we rely on the momentum equation for a single particle. So, in this particular case, the x component of velocity, which we can denote as u infinity now, is basically constant and is given by this expression. So, next we can solve the two momentum equations, basically integrate with time, and you get a similar expression in both cases. So, in this case, for example, we get this expression. So, if we put this condition that t tends to infinity, then we see that the axial component of velocity basically boils down to this expression. So, what would you get if theta is equal to 0? That is, we have a horizontal channel. Then in that case, this is u infinity, that is as expected. But because here the channel is at some inclination, so the final velocity wouldn't be equal to this, but this factor less than the free stream velocity. So, this is a quick check to see if you are getting the correct answer. Similarly, for the y momentum equation, solving y momentum equation, we get the expression for the component of velocity in y direction. So, in this case, if we put the same condition, we get Vy is equal to minus particle relaxation times the acceleration due to gravity times cos theta. So, in this case also, if theta is equal to 0, what do we get? Minus tau dg. Why we have minus sign? Only because the coordinate that we have chosen. Okay. So, the acceleration, the component of acceleration due to gravity is opposite to the y direction, and we get this. What is this? Particle relaxation times the acceleration due to gravity. This is settling velocity, particle settling velocity, terminal velocity basically. Okay. So, then how do we find the minimum length of the channel that ensures that all particles have settled? For that purpose, we have to calculate the time that the particle would take to reach to the bottom of the channel. And here we are considering the particle which is injected at the highest position, that is, which is injected at this location, because this will take the longest time to settle. So, for that purpose, first we have to solve the y momentum equation we have to solve, we have to integrate this equation for y component of velocity and get the expression for y. And then if we put y is equal to 0, then we will get the time required for this particle to settle, and you get this expression. So here the Tf is unknown, which can be found from this equation. Now, if we consider this case where the time of settling is much larger than the relaxation time, this means that the particle adjusts with the flow quickly compared to the time that it takes to settle down. Then in that case, we can show that the settling time is basically equal to h by tau dg cos theta. Now, what is tau dg? Again, that is the terminal velocity. So again, in this case, if we consider that theta is equal to 0, if we assume theta is equal to 0 or a horizontal channel, then what do we get? The height divided by the terminal velocity, which is again as expected. Distance divided by the velocity. Why terminal velocity? Because in this case, the particle is reaching the surrounding fluid velocity quickly under this assumption though. Okay. So this is again a check to see if we are getting the correct answer. What is the next step? So from here we solve for this time Tf, and then we need to, once we know the time, then we can integrate the x component of velocity and integrate that from 0 to this time, and then you get this simple expression. And in this case also, if we use this condition, we can show that basically this L is equal to this. So here this Tf itself is to be obtained from this expression, So if we use this, then it is possible to show that under this condition, L is equal to h times this parameter. Okay. Next, how do we calculate the settling rate? So what is meant by settling rate here? The rate at which the particles approach the bottom wall, that is basically the settling rate, we can say. So now how do we calculate that? For that we need to do a mass balance. So here you see this is the bulk velocity of the particle times the projected area, assuming that W represents the dimension perpendicular to the plane of the paper, times the x component of velocity at some location x, minus the same quantity at some location x plus delta x. So the remaining quantity must be coming down, okay, and this is basically equal to this. That is the flux of the particles in y direction times the area. So if this is delta x, then this area is W times delta x. So if we simplify this, we get this expression, and this is nothing but the settling flux. What is settling flux? The mass of particles which are settling per unit area per unit time. So from here again we can, so what is our objective? Our objective is to get an expression for this term. So then we can expand this and then rearrange this to get this form, and finally we can show that we can get an expression for the bulk density in terms of time. Why? Because from here we could show that the left hand side is a function of bulk density, while the right hand side is a function of Vx and Vy, both of which are function of time. So, if we integrate this, we will get bulk density as a function of time. So, here we have to remember that the bulk density is not constant. What we have calculated earlier is the bulk density at the entry. Okay, actually the bulk density is not constant. Why? Because particles are getting settled down. So, once we know the bulk density, how it varies with time, we can calculate the settling rate by integrating this expression. Okay. If you want to get an expression for settling rate as a function of space or distance, then you can get expressions for Vx and Vy also in terms of x. So, you can eliminate time basically. Okay. And then finally get the settling rate as a function of this spatial distance. Okay. So, this parameter will give you the total settling rate, okay, or the total amount which has settled. Okay. So, after this we will go to another example. So, this example is on particle deposition on a flat surface. So, this kind of applications are encountered in various fields, including thin film coating, drug deposition, spray painting, additive manufacturing, semiconductor chip fabrication, etc. So, particle deposition on flat surface occurs in many applications. But here what is that we are trying to do is, our interest here is to determine the critical particle size which is necessary to guarantee deposition on the surface without lateral drifting. So, now what is meant by lateral drifting? So, here for example, you see this is a nozzle, and let us say this issues an air jet, and this air jet hits a flat surface. So, here you can see the streamlines. Now, imagine we introduce some particles here. So, now what do we want to find out is, what is the particle size which will get deposited at the surface. If you assume that once the particle reaches the surface, it is deposited, which also may not be strictly true, but let us assume that once a particle touches the surface, we assume that it is deposited. You may think why that should not happen. So, that may not happen if the particles are drifted away. Imagine the particle size is very small. Then here you see the streamlines of the airflow. The small particle may not get deposited, but rather it just drifts away laterally. Okay. So, that is possible. So, now if you go on increasing the particle size, then what will happen? Intuitively you can imagine, if we go on increasing the particle size, the tendency for drifting will be lower. So, now what is the critical particle size above which it will always deposit? That is what we want to find out. Okay. So, for that, first of all, we have to calculate the flow field, as in all cases. So, in this module we are considering all problems where the flow field or carrier phase field is prescribed. So, in this case we can consider a potential flow solution, and it is easy to get this expression. So, this is the stream function where this constant B basically depends on the operating condition of the nozzle and the geometric parameter. So, here this parameter uj is the exit velocity, T is this, the diameter of the nozzle, and H is this height. So, here for simplicity we are considering a two-dimensional jet. What is meant by two-dimensional jet? This distance, the geometric parameter, okay, is much smaller than the width of the jet perpendicular to the plane of the paper. So, it is a two-dimensional jet. For simplicity, we have considered this, but one can also consider a round jet. So, the potential flow theory gives this solution. So, we get a hyperbolic function that represents the streamlines, and these are the streamlines which are shown here. So, once you know this, then the next step is to consider now the particle equation of motion. So, here we can you can see the particle equation of motion. Here you replace ux and uy with these expressions, and then we can solve this. So, in this case we have the acceleration due to gravity in the y direction. So, if you solve this, you can get the particle trajectory, and here some results are shown. So, here you see the particle trajectories for the particle size ranging from 1 micron to 10 micron, and as expected, as you increase the particle size, so this is particle size. So, as you increase the particle size, its trajectory shifts towards left. So, for example, this 1 micron particle, it perfectly follows the streamline. This means that if you calculate the Stokes number of the particle, of that particle, 1 micron size particle, it will be much smaller than 1. But as particle size increases, the particle trajectory deviates from the streamline of the carrier phase flow. And here interestingly, it is found that for particle size with diameter around 8 micron is the critical limit. So, particle size beyond 8 micron would ensure that it is deposited. So, here what is shown here is that once the particle is deposited, then what is the area it will create, and how that area would change with particle size. So, if we use larger particles, then the effective area of deposition would decrease, and that is what you see here. However, here you do not see a monotonic reduction. That is interesting. So, this as you go on increasing the particle size, it will reduce, but so initially it reduces significantly and after that very slowly. Okay. And for this one, there is some experimental evidence present, as you can see here. So, these are photographs of a spray which is generated from an ultrasonic nozzle which has size range, means we can control the size range, you can imagine like that. So, in this case 2 micron particles or mean diameter, average diameter is 2 micron particles. So, here you see the drifting of the particles. However, in this case when we use around 8 micron particles, mostly it is deposited, which is a very good validation of the simple theory. Okay. So, finally, we consider this example of particle vortex interaction. So, interaction of particles with vortical flows occur in many applications, including environmental atmospheric flows, combustion, drug delivery, in general all particle laden turbulent flows, because a turbulent flow, you can imagine that a turbulent flow consists of eddies of various sizes, So if we put particles in that, then the particles would obviously interact with those EDs. So here the objective is to demonstrate that. So for that purpose, we consider a model vortex, which is known as Rankine vortex. I am sure you are aware of Rankine vortex. So Rankine vortex basically is a simple model which refers to an idealized case of the real vortices, which combines the features of both forced vortex, which is solid body rotation at the central core region, and the free vortex away from it. So here you can see the example. So here if we plot the velocity, it will look like this, something like this. So the first you have solid body rotation. So within a critical radius, it behaves as a solid body. So the tangential velocity is basically equal to r times omega, where omega is the angular velocity. So that is why it increases. And then we have free vortex, where this gamma is basically this circulation, which is also dependent on the angular velocity and this radius. So this radius has to be specified. So as you can see, for given radius and angular velocity, the circulation is fixed. So as you move away from the center, the tangential component of velocity would reduce, as it happens in a free vortex. Okay. For example, a whirlpool. However, in this case, the radial component of velocity is 0, and maximum velocity, tangential velocity, is realized at this radius RC. Okay. However, this is only a model. This does not represent reality. Why? Where is the technical problem? If you see, the technical problem lies here. So here we have continuity in velocity, but not in the gradient of velocity. Practically, it cannot happen that at this point you have positive gradient and negative gradient at the same time. Okay. So that is the limitation of this model. But for our purpose, it is fine. So here what do we want to do is basically we want to release one particle somewhere, say here, and we want to see the trajectory of the particle. What would happen to this particle? We can give any initial condition that we want. For example, we can release the particle from 0 velocity. In this case, we are releasing the particle such that the radial velocity is 0, but tangential velocity is equal to the local fluid velocity there. And let's see what do we get. So for that purpose, we have to consider now the particle equation of motion, but in polar coordinates, cylindrical coordinates. So now here you see this is straightforward. As you can see, in polar coordinate we have this term present. Now if you look at the acceleration terms, we have these additional terms coming into picture. However, we should remember that this does not represent as such any external force. This is a consequence of using the polar coordinate system itself. So actually, the acceleration in the radial direction is this quantity minus this quantity. That is actually the radial acceleration. So similarly, you combine these two quantity, that represents the tangential acceleration. Okay. So the forces what we are considering here is only the drag force. And also, as I said, we have given this initial condition. So the particle trajectory behaves like this. So if you release a particle somewhere here and imagine this is your vortex, then the particle trajectory would look like this. I will show the trajectory in the next slide though. And here this shows the radial velocity of the particle with respect to the radial position. And this shows the tangential velocity of the particle. So as I said just now, so this is the profile of the fluid in the radial direction as expected, because here you have solid body rotation, it increases, and then free vortex, it decreases. But this particle is unable to reach that. Okay, this means that it's a small particle or a large particle. If it is a small particle, that would always follow the fluid. So it would have followed this. But we see a departure. This means that the particle relaxation time is higher. And that is what we see here in fact. So this is what I wanted to show, but it was an animation. You could see the particle moving like this. So here we have considered 3 particles. One is 100 micron particle, and you see it is there everywhere. What does it mean? This means that it is closely following, so same particle is released. It is closely following the streamlines. So once released, it undergoes this vertical motion till it exits the computational domain. If we have 1000 micron particle, you see how it behaves. Okay, so this is unresponsive to the fluid motion. So obviously the fluid motion influences the particle trajectory, but the response is not good. So that is why you see this trajectory. On the other hand, if we have 500 micron particle, up to some extent we see the departure, but after some time you see that again it is kind of following the fluid streamlines. So this means that somewhere here it has higher Stokes number, and as it has moved out, its Stokes number has reduced. So this is a very nice example, and this shows the quantitative picture of what is presented here. So the radial component, radial velocity and tangential velocity, how it varies with the radial position. Okay. Okay, so we have discussed as of now various examples of particle-laden flows where we predict the particle behavior when the carrier phase is prescribed. So if you see overall, it's a 2-step approach. First, you have to develop the physical model, and you need to make suitable assumptions such that the main essence of the flow is intact. So for simplifying, you make some assumptions. For example, in the case of the flow past a human being where he or she is coughing, that case, we assumed uniform flow throughout. Okay. But obviously the flow is not uniform. So if a person is standing and there is a flow past this, past the body, then the flow cannot be uniform. There is flow separation, all those phenomena happen, right? But we have neglected those. Okay. So like that you have to do simplifications. Okay. So developing the physical model, okay, is the first step, and it is the most important step. The next part is how to solve the equations. So solving equations is not a big task or a challenging task here, because here we are not going to do high-end computations. So once the formulation is correct, and that is what is very important, then you can do the solution. You can write, for example, a MATLAB code to get the solution. Okay. So what we see here is that the approach is very simplistic. Our approach was very simplistic, but still it provides lot of insight into the flow, into the particle behavior, okay, without doing any extensive numerical simulation or experiments. Okay. So the purpose here is to, in fact, provide first-hand estimate of the flow, which will help in designing the computational simulation or experiments. Okay, so that is the main objective. So throughout we have assumed that the carrier phase is prescribed, but is it possible for all cases? If no, what shall we do? So that is what we will see in the next module. As I mentioned, prescription of the carrier phase is not always possible. It is possible only for special cases, as we have seen. So it is possible when we make some strong assumptions. First one is one-way coupling. Whatever problems that we solved, we always assumed one-way coupling. The particles don't influence the fluid. Second, we have assumed laminar flows. Then we have assumed simplified flows. For example, this transport of respiratory droplet that I just talked about. Then also we have considered canonical flow configuration. Means, let's say flow past a body, on laminar flow past a body, let's say, or say flow over a flat plate, or flow in a channel, okay, for which the solution exists, the fluid flow solution exists. Only those cases we can analyze it this way. Okay. However, in reality, we encounter complex geometry. There is two-way coupling present, and we have turbulence. There can be many other factors, but these are the three main factors which we didn't consider. So, first, if you see complex geometry, what is meant by that? We have solved, for example, Poiseuille flow in a pipe. So we know the profile. But let's say it slightly expands and you have a flow like this. You have a configuration like this. Then we cannot solve it theoretically, right? Or let's say you have flow in some tubes. Okay. This is also theoretically you cannot solve. Now let's say you have flow over flat plate, that we know we can solve for laminar flow. Now let's say there is some wedge or some protrusion here. Okay. Then what to do? And all these are common in engineering applications as well as natural applications. Okay. So we do encounter with complex geometry, and these are also not super complex. So a simple deviation from the canonical configuration puts us in trouble. Trouble in the sense we cannot theoretically solve. We have to now computationally solve the governing equations. Okay. So now what are the governing equations? To summarize here, these are the equations for incompressible non-reacting flows that we had already discussed. So now the question is, can we use the same set of equations for complex geometry? The answer is yes. Yes, we can use the same set of equations. Okay, now you have to modify the boundary conditions. More complex boundary conditions come into picture, but still it can be taken into account. Next, if we have two-way coupling, can we use the same set of equations? The answer is no, unfortunately. Why? because the particles would now influence, for example, droplet evaporation. So, the particles evaporate and add mass to the carrier phase. So, you have to account for that. So, that effect must be accounted in the continuity equation. And particles offer drag force on the carrier phase also. It is not like only the carrier phase would drag the particles. The particles would also apply equal force, Newton's third law, on the fluid. So, this has to be modified. Similarly, when you have heated particles or there is any kind of heat transfer, then between the two phases, that also must be accounted. So, this means that the same equations we cannot use, first thing. Second, now when we have turbulence, can we use the same equations? If we have turbulent flows. So, when we have particles, then it's a different flow, we can understand. But now let us say there are no particles, you have flow, fluid flow only, but it is turbulent. Can we use the same equation? The answer is yes. Why should the equations change? For example, continuity equation. Why should continuity equation change? Only because the flow become turbulent? No, it won't change. Or Navier-Stokes equation or energy equation, it won't change. But we cannot directly use, or it is not easy, let me put it that way. It's not easy to directly solve the equations if we have turbulent flow. We have to bring in some kind of modeling to account for turbulence, though it is not essential. Okay, so finally, what we learnt now is that the carrier phase governing equations must be solved to evaluate spatio-temporal variation of the fluid flow. So, now we will look at modeling two-way coupled flows. So, now let us consider a dispersed multiphase flow like this. So, here now you have particles in the flow and you want to solve the equations. Now, you have to solve the equations for both particles as well as the carrier phase flow. Now, then what we need to do? We need to, how do we solve this? By considering the boundary conditions. So, we need to consider the boundary conditions at the surface of all particles. For instance, let us say instead of so many particles, there is only say one cylinder. This problem we have done in the past, right? So, there is flow and there is one cylinder here. So, now how do you solve this, the equation for the fluid flow? You introduce this boundary condition, that no slip boundary condition prevails here. And that is what you introduce and solve the equations. How you solve it, that's a different thing, but that is how you solve it. Now you imagine there are many particles, okay, and for a moment you assume that the particles are stationary and the fluid is moving. So, this means that instead of one cylinder, you have many cylinders in place. Now, how different is the problem? That case where you imagine there are many cylinders which may be arbitrarily positioned and the cylinders are fixed and but the flow is happening. So, the only difference now is that you have some extra boundary conditions. That is the only difference. Okay. But now you come to our case. So, in our case what happens? The cylinders are not stationary, but they are also moving. So, this means that the particles, the position of the particle changes at every instant of time. Okay. So, it is not only that you need to provide the boundary conditions to solve the fluid flow equations, the boundary itself is changing at every instant of time. Okay. So that is a problem. Now, this means that the particle and the fluid equation must be simultaneously solved. Why? Because now the particle is offering drag to the fluid flow, but the fluid flow is causing the particle to move. So this means that we have to solve the equations at the same time. Okay. But particle position must be updated at every time step. Okay. But do you know the particle position beforehand? So you start with some particles, okay, but you have to calculate in the next step where the particles are, and then again implement the boundary condition there. So this means that this must be iteratively solved. But there are millions of particles in your flow in any practical case. So the question is, how would you solve this? So it is not like you cannot do it. So what you need to do is that you need to give new boundary conditions at every time instant and solve the two equations simultaneously. But you have to do it for millions of particles. So this is challenging even if we consider the simplest case. What is the simplest case? Simplest case means you have some, let's say, solid particles in your flow. Particles are perfectly spherical. Let's say particle size is also monodisperse. Okay. The particles are not deforming, no heat mass transfer, no chemical reaction, no particle collision, no particle wall interaction. Yet it is extremely challenging. Okay. So this approach is known as fully resolved approach, okay, where you completely resolve the flow. So you have to resolve the flow. This means that your grid size, if you want to solve this numerically, your grid size must be smaller than the size of the particle. So, for example, this is what should be the grid size. So you are resolving the flow around individual particles. Then only you can couple them. So then only you can bring in the force that the particle exerts on the fluid. So what will be that force? That will be here. You have to integrate the force at the particle interface along the surface or throughout the surface. If you do that, then you get the total force due to that particle at that location on the fluid. Okay. So this now, if you have, let's say, 10 micron particles in your flow, this means that your grid size should be in nanometer range. Okay. So that is the reason why the computational cost is high. It is almost practically impossible to analyze such engineering flows. Okay. Here it need not be restricted to engineering flows, even let's say natural application, let's say cloud formation. So in cloud formation, you have basically interaction of the droplets. Once the condensation occurs on aerosol particles, you have droplets. Then those droplets interact with the surrounding flow. There also you have similar scenario. You have millions of droplets. How will you compute? It is practically impossible. But does that mean that this approach is of no use? The answer is no. We can do computational simulations with fewer number of particles, which would provide deep insight into the flow physics, and also it is useful for development of models for other approaches that we will see sometime later. Okay. So this is all about fully resolved approach. Okay, so time is up, so we'll stop. We'll continue this in the next class.